All right, so we're going to look at the effect of different bases on our logarithmic function. Since these are inverse functions to exponentials, we're going to take a look first at exponential functions. So we have here four graphs. The graphs of 2 to the x, e to the x, 5 to the x, and 10 to the x. And hopefully you remember that the faster or the higher the base, the larger the base, the faster things grow, right? So 10 to the x is growing super fast. And in fact, we see the point 1 comma 10 on here. So we know that this is 10 to the x. 2 to the x is growing slower, right? We would have the point 1, 2, 2, 4, 3, 8. So we know that this one is 2 to the x. And therefore we know the others as well, because the larger the base gets, the closer we stick to the x-axis or the y-axis. Because the faster it grows. So this gray one's going to be 5 to the x. The green should be e to the x, right? And then we got them color-coded here. Okay, so kind of the same thing with our logs, right? So remember that our logarithms are reflections across the 45-degree line. So there's a very poor 45-degree line. So since we're reflecting, we know the point, if the point 1 10's on here, then 10 1 would be on log base 10, right? And the point 1 0 would be on there too. And so we can see, here's my blue one. It's going to be my log base 10, so log x, right? 10 to the x was closest to the y-axis, so log base 10, or common log of x, is going to be closest to the x-axis. Then same kind of thing with 2 to the x. 2 to the x was the slowest growing of this group, so it is further from the y-axis. So log base 2 of x is going to grow more quickly, right? Plus we know 2, so we've got 2 to the 1, 4, 2 to the 2, 2 to the 3 is 8, right? So that we know that this is log base 2 of x. And then, of course, by kind of elimination, we can say, this is log base 5 is the gray one, and ln of x is the green one. So we're seeing here, the larger the base, the more slowly the function increases, the closer it is to the x-axis. And there's actually something that we use in, I won't call it everyday life, but that pretty much everybody is familiar with, that is measured in log base 10, and that is earthquakes, right? So if you've been out in California or Alaska or any other part of the world that has commonly has earthquakes, you know that like a 2-point something or 3-point something is really not much of an earthquake. And in fact, about 15 years ago, we had a 2-point something or 3-point something earthquake, I think it's either Tennessee or South Carolina. And I actually was, being on the 4th floor of the University Center, I felt it just a little bit. I was like, either I got a little bit of vertigo or the building was shaking. And the only reason why I noticed was because I was sitting and I was being still. And so I just noticed a little bit of vibration. But so a 2 or 3, not much to that kind of an earthquake. But a 5 is pretty significant, and a 7 is catastrophic, right? Because a 7 is going to be 100 times worse than a 5. So, at any rate, let's go into our last example here. We have a lot of things going on this one. So we want to know how the graph can be obtained from the graph of a basic log function. So first, what is our basic log function? Our basic log function, is going to be log base 2 of x. All right, so we can look at this, and the first thing actually we want to do is fix this inside here. So we're going to say log base 2, I'm going to pull out a -3, okay? And I'm going to do x. So I got -3 times x, that's fine, that's this part. And then -4, right? And that gives me the plus 12 that's in there. Because that's going to help us determine our transformations, all right? So our first transformation now that we can see is a shift to the right by 4, right? That is this part, the x minus 4. Then we know we've got this 3 attached to the x, right? So that is going to be a horizontal stretch. This one's a tough one. So horizontal stretch by 3, by a factor of 3, and we've got a reflection over the y-axis because of that negative. And then, of course, lastly, we have a vertical shift down by 3. So those are all of our transformations. Now, is any of that transformation going to affect the range? No, because it's all real numbers, and you can move all real numbers away around all that you want. It's still going to be all real numbers. Okay, so let's look. We're going to start with y equals log base 2 of x. So we know, let's see here, 8,3, right? So here is our log base 2 of x, right? So y equals log base 2 of x. Okay, so what are we going to do first on this thing? It's really kind of your choice. You can move it 4 to the right, or you can flip and stretch first. I think it's easier. So PEMDAS says move it 4, and then you can reflect and stretch across not about the y-axis anymore, but about the vertical axis, x equals 4. I feel like it's easier to do the reflection and the stretch or compression first. So we're gonna do that. So we're going to do our second one. We're going to say y equals log base 2 of negative x. Because what is that going to do? That is just going to reflect this thing across the y-axis. So we can say, okay, great, we're going to have this, right? That's going to be our y equals log base 2 of negative x. Okay, then we're going to say, okay, great. We're going to do log base 2 of negative 3x. We're going to do the stretch. Now this one, this is actually not a stretch. It's going to be a compression because our input is growing kind of 3 times as fast. And I'm going to rewrite that in purple. So basically each one of those points is going to be roughly a third of where it was. So we're going to have, so this point's going to move here, and we're going to have 2/3 here and 4/3 here. So it's going to look we're going to look at GeoGebra for this in a minute. So this is, we've got y equals log base 2 of negative 3x. All right, now we can get to the easier transformations, right? Log base 2 of negative 3x minus 4. So we're going to take that purple one, we're going to move all those points over by 4. All right. So we're doing that in green. So far our vertical asymptote hadn't changed, but that thing's going to move over now. It's going to move 4 to the right. So here's our new vertical asymptote. We can go ahead and write that down. X equals. And so each one of these, so instead of being negative 2/3, is going to be about here, right? 1, 2, 3, 4. Yep. And this one, instead of Instead of 4/3, we're going to be about here. And at that point, I'm just going to call it, oh wait, I'm off by a little bit. Here. And then we were here. No, I wasn't. And then we were here. Close enough. Oops. So we're doing that, right? Close enough. Kind of that horizontal compression. So that's our green one. Log base 2, -3, x minus 4. And then we need one more color. I guess we'll go with black. And then we're going to go down on that one, right? We're going to say y equals log base 2, -3, x minus 4, minus 3. So we're going to take all those points and go down 3. 1, 2. So one here, one here, one about here. And we can see there's our final plot. Y equals log base 2, -3, x minus 4, minus 3. So what's our domain on this one? Between the reflection and the shift to the right, we're looking at -infinity to 4. So let's look at that. I know this one's going a little long, but let's look at that in GeoGebra and make sure that we did everything right. Okay. So we started with log base 2 of x. And so you can see there's our graph, right? And then we said, okay, we're going to apply the negative, so log base 2 of -x. There's our reflection. All right, then we do the next one, right? Y equals log base 2 -3x. So that kind of squished it, right? Compressed it a little bit. All right, so we've got log base 2 of -3 times x minus 4. Now that did our shift to the right. And then log base 2 of -3 times x minus 4 minus 3. So there's our green one. And just to make sure, we're going to do log base 2 of 12 minus 3x minus 3. And those are the same graph. So we definitely did this right. And what we drew here, we followed each one of our transformations one at a time to figure out where we were going to end up. All right. And that is finally it for this one. I'm sorry it ran a little long.